Hi, and welcome to our discussion on the fundamentals of consolidation. This presentation is brought to you by Josh, Brandon, Marco, and Josie.
To begin, I would like to give a brief overview of some of the topics we will be discussing. First, we will define consolidation, and then we will discuss time rate of consolidation, settlement, and why this knowledge we are providing is useful in real life. Consolidation involves the loading of fine-grained soils that are 100% saturated. This means that the space between soil particles are filled completely with water, and no air is present. These conditions are an important factor in consolidation, since fine-grained soils do not allow water to pass through them quickly. And since water is incompressible, the water present will initially bear the entire weight of any loading that is placed. As it can be seen in this short animation, when loading is placed on a saturated soil, the water present will seep out of the soil, and the soil particles will move into a denser configuration. As more and more water leaves the system, the soil itself will support more of the load.
Now on to the time rate of consolidation. The time rate of consolidation is exactly what it sounds like, the rate at which consolidation occurs. There are many factors at play, some of the minor ones being the initial void ratio, the gravity, the compressibility of the soil, the density of the water within the layer. But the main factors and the ones that we're going to be analyzing is the permeability of the soil and the drainage length. Of course, the more permeable a soil is, the faster water is able to drain out of the soil, resulting in a faster rate of consolidation. Now, as for the drainage length is the length of the longest possible path that a water molecule within a soil layer will take in order to drain out. This is actually affected by the permeability of the surrounding soil layers due to the fact that water will always seek the easiest path to take. And of course, the shorter that our drainage length is, the faster the rate of consolidation. Because if water has to travel a less distance in order to drain out, then of course it's going to drain out much quicker. Now let us look at a quick little example in order to further understand this. Here we have two scenarios. In both scenarios, we have 3 layers of soil. We have a profile view of 3 layers of soil. And we're only going to be analyzing the consolidation of the clay layer, because consolidation only occurs on fine-grained soils, not sand nor bedrock, because they are considered incompressible. Now looking at scenario 1, we have a sand layer above and a sand layer below. It is common knowledge that sand is more permeable than clay. Therefore, because of the fact that water will always seek the easiest path to take, and that is in this case towards a more permeable layer, a water molecule will either seep out through the top layer or the bottom layer. And therefore, our drainage length, which is the longest possible path that water will take, would just be this distance right here, which is the length of our layer divided by 2. And because our water in our clay layer seeps out through 2 directions, we consider the clay layer to be doubly drained. Now on to scenario 2. In scenario 2, we have a sand layer above and bedrock below. Sand is more permeable than clay, but bedrock is less permeable than clay. Therefore, water will not seep out through bedrock. And because of that, the longest possible path that a water molecule within this clay layer will take is this one, is right here. And because it only seeps through 1 layer, we consider this clay layer to be singly drained, and our drainage length is just the length of our layer. I hope that helps you better understand. Thank you.
I'll be talking about the settlement due to consolidation. And consolidation settlement is time dependent on mostly just the time it takes for the expulsion of water from the voids, and then the compaction due to the force on top of it, usually caused by a building or such. As water exits over time, the volume of soil shrinks, since all the space that was taken up by the air and water is being forced out. The soil that is caused by the loading and the direct effect of consolidation.
Why is consolidation important, and how does it affect you? Given that consolidation is a process that can take place over a long period of time and plays a huge role in structural stability, it is an important factor to keep in mind when thinking about the use and lifetime expectations of a structure. Some examples of consolidation can be seen in structures that begin to crack or tilt, such as the Leaning Tower of Pisa. And although these forms of deformation do not always look this significant, they can lead to serious structural integrity issues. So be on the lookout for signs of cracking or tilting on your local structures and ask yourself, could this deformation be due to consolidation issues? Thank you for watching, and I hope you enjoyed our conversation on the fundamentals of consolidation.